Girls, today we're going to combine metric conversions and expressing numbers in scientific notation. Right? We're going to need this chart, so get that out. I posted to Google Classroom just this morning your work for today. For various reasons, I had to give it to you as a PDF document. So either write these down or print them out if you can. And I think that should be it. Okay, let's start here by just doing an example problem of just strictly metric conversion of regular numbers, not scientific notation. So get this chart out, this metric ladder chart. Let's say we have the measurement of the mass of a tiny speck of dust. All right, it's going to be small, 0.00076 grams. All right. Now, numbers that are really this small, we really ought to use a more convenient unit of measure, something like a milligram. How many milligrams is that? Milligrams are typically used when you're measuring small things. All right, let's do this conversion real quick. Grams to milligrams. Well, grams is the base unit. Milli is 3 steps below. And since we're going down, it's 3 to the right. So we're going to move this 3 to the right. So it's going to end up right here. So it'll be 0.076 milligrams. Okay. Now, here's where we're going to start dovetailing into this discussion, scientific notation, writing numbers in scientific notation. Let's, for right now, just forget about this side of our little work here. Pretend I was asking you just solely on this number. Express this number in scientific notation. Well, standard notation has us reposition our decimal point so that there's a single non-zero digit in front of it. So we're going to take this number and write it down as 7.6 times 10 to some exponent. Okay. The value of the exponent up here is exactly equal to the number of places we had to move our decimal point to get it between the 7 and the 6. That's 1, 2, 3, 4, 5 places. So this would be 10 to the 5th. However, if we're moving our decimal point to the right, it's a -5. Something you ought to keep in mind right up front. And it's a lot easier than remembering if you move it right, make it negative. If you move it left, make it positive. This number up here is really small. All right, 0.000076. That's a small number. When we express small numbers as a number in scientific notation, we're always going to end up with negative exponents. All right, that's the easiest way to remember it. Small numbers end up with negative exponents. All right, so there we have 0.000076 grams is exactly the same as 7.6 times 10 to the minus 5 grams. These two numbers are the exact same number. They're just expressed in two different ways. The scientific notation or exponential notation is something you need to know if you're going to stick around and be a scientist or an engineer or a doctor or, anybody who uses math and science a lot. All right, now let's do the same thing for this side. All right, let's forget about what we just did there and take this number, 0.076 milligrams, and express it in scientific notation. Again, we want to reposition the decimal point so it's between the 7 and the 6. 7.6 times 10, and the number above the 10, the exponent, is exactly equal to the number of places our decimal point got shifted. Between this position and this position, we had to move it 2 places, so it's 2. But again, since we moved it to the right-hand side, it's a -2. It would be milligrams. Again, I can also say this is a small number, and small numbers always have negative exponents. Okay. Now, these two expressions are exactly equivalent. All right, 0.000076 grams is equal to 0.076 milligrams. 7.6 times 10 to the minus 5 grams equals 7.6 times 10 to the minus 2 milligrams. They say the exact same thing, both of them. Now we've learned how to do metric conversions here. How do we do metric conversions when our original number is given in scientific notation? In other words, what if we weren't able to see this up here? And I simply asked you, right, what is this number converted to milligrams? Well, this number converted to milligrams is this, of course, because we already got that. But in each and every case, it's always going to be the exact same number, and the only thing that's going to change is the exponent above the 10. Take a look at these, front or left and right side. 7.6, 7.6 times 10, 10. This is a minus 5, but this was a minus 2. How do we determine that all on its own if we didn't have that upper problem to start with? All right, let's take a look at how we could get that. Now let's put the negative 2 back in here, and I want to just point out to you something. All right. What is the difference between these two exponents? Mathematically, what is the difference? It's 3. Right? Just think of a number line. You have 0 here, -1, -2, -3, -4, and -5. By difference, we are really asking ourselves, how far apart is -2 and -5? Well, just look here. If you just jump from one to the other, it's 1, 2, 3. The difference is 3. All right. Now here's the real shocker, the real eye-opener. Our original conversion was from grams, which is the base unit, to milligrams down here. How far apart are those? 3. How far apart are these exponents? 3. All right, so I hope you could see what's going on here. Okay. Let's try another example.